Hello, everyone. My name is Malik Mохrat, research engineer in Sber Robotics Center in the team of Perception and Navigation. Today, I'm very excited to walk you through the topic of how robots reason in the world. That is how we build 3D structure. It's semantic representation that we call knowledge slum. To define knowledge slam, we all know that the traditional slam systems lack the semantic knowledge. So they construct a metric map that only answers the question where I am. On the other hand, a knowledge slam system can answer several questions, including where I am, what I see in front of me, how these objects are related and locate to each other, and we know the in the natural language, the labels, how we call each of these objects. So we build a metric semantic 3D representation. This is very important for the robot because it makes the things easier for a planner, global planner, that can interact directly with such kind of memory or representation of the scene. It can interact directly using natural language, and it makes the semantically easy to locate. It makes easier to locate the robot semantically this time, not only geometrically within the map. This is also important for ML researchers because we are deploying these foundation models in structured settings in robotics platform, embodied one, and solving such kind of task such as semantic segmentation, captioning, and so on. There might be several benchmarks that could be beneficial to the community. It also matters the society actually because this brings us closer to having the so-called general purpose robot system that is able to see, plan, to memorize only just only as we humans do during our daily life. So after we knew the definition of the knowledge slam and why it's important, let's check where it's located in a robotic system. So actually, a knowledge slam system sit directly between the intersection of perception, mapping, and the planning, where it gives knowledge map to the high level, long, high level global policy to give it a long term memory so that we can plan the task, and the planner gives commands to search and locate to within the map. This could be using natural language because we save this information within our map, and also it helps to relocalize actually the system within the robot within the map. Okay, now we have knowledge. Where to to store such a knowledge? Basically, we use graphs for this, where the nodes are the objects combined with their properties. This could be caption, this could be crop, this could be some features, embeddings about these objects. And also, the edges are the spatial relationships between these objects in the environments. To get so, we use several foundation models to construct such a graph. as we see here in the picture, where we have graph of hierarchical graph actually that represent first of all floors. Each floor contains the several places or rooms. Each room contains several objects. How are they located to each other? Is near, contains, and so on. So to get basically such graph, we need to study several skills or tasks to be afforded to the robot, such as semantic segmentation, captioning, to understand the special relation, to be able to build local knowledge only from one image, and then to make a global graph such as this of the whole scene using fusion of these local graph, and to do visual grounding actually to localize and to retrieve object within the map using either textual or visual queries. Basically, we studied several baselines that solve this task, such as concept graph that indeed builds open vocabulary scene graph. They also integrate planning ability within their pipeline, but their drawbacks basically was that it's competitionally hard due to various models that they use, and they assumes static scene, so they are not able to work with dynamic environments. On the other hand, RoboHop didn't use the 3D representation. It relied only on 2D representation using semantic segmentation. They added the ability of query, open vocabulary query, but it also struggles from scalability concerns, so it may not be able to map big environments. Clio, on the other hand, it's a task-driven graph creation method that works indeed in real time, but it's in some kind has some prompt sensitivity, and maybe it's not be able to work if we give a complex task in this case. Our system, basically, on the other hand, consists of three main components, which are knowledge perception, knowledge mapping, and knowledge search. The knowledge perception modules use several foundation models and VLMs to generate local graphs from a single image, so that we get an annotated frame with some metadata about objects, about the context of frame, about how the objects are related to each other and their spatial relation. While the knowledge mapping generate the graph, the 3D graph representation using 3D fusion, multimodal 3D fusion by object-centric algorithm of mapping. The search is able to make object retrieval within this knowledge map. It is the planning, and it makes the place recognition task of or relocalization within the map also available. We have here an over to view the schematic view of our system. We have the input as posed RGBD image. We have our perception system which contains of some modules. For example, semantic segmentation, how we annotate the images, how we get the initial graph from the caption that we get from VLM. Then we enrich this initial graph with some information, more information actually, about these objects such as centroid, captioning, and so on. After that, we get the local knowledge that can be merged together actually through object-centric 3D knowledge mapping system to get a 3D knowledge map. As we see here that our system basically is modular. We can avoid some stages or some task here or extend it. We develop all of that so-called knowledge framework, where we have several interfaces. One of the core interfaces within the system is interface for stage, which is responsible to, each stage is responsible to extract some information from the observation that we have. These stages could be related to objects or could be related to edges. For objects, it could be semantic segmentation, it could be captioning, encoding. The context stage is to get the whole context of the frame, while for the mapping pipeline, we have the builder interface, which expand the knowledge map from the local observations to get an overall graph. And there is an interface to search by textual or visual queries to locate objects within the map. So we will start to dive in more details about our pipeline of knowledge perception, where basically we get such a local graph only from one RGBD posed image, and that we first of all make semantic segmentation using any open vocabulary and foundation model one, such as sound, for example. Then we annotate this based on this mask, our frame, using sum or set of marks. Or we feed the VLM, in this case it is ChatGPT 4o, to get a context out of this image. Then we use an LLM to get like initial graph that we enrich each node of this of it by information about objects, its centroid, for example, knowing the point cloud of the we make actually a point cloud out of the depth, and knowing the intrinsics of such a frame. We also may caption only the crop of this object using mobile VLM, for example, model to make things faster. We also get embeddings for each object by using encoder such as clip, such as Dino version 2. And we also can get anthology, some information about the anthology of the object, where we answer using VLM some questions about what color is the object, is it movable, is it open, for example, like a certain amount of questions for each object. To make the things easier for the planner. Of course, we can avoid any stage of these, but the overall results will be stored within this local knowledge graph. So I have mentioned one important technology that our pipeline include, which is SAM-SOM. We call it SAM-SOM. First of all, we do SAM segmentation, and then we add to it SOM, which is based on set of mark work, where it's basically instead of feeding a raw RGB image, we feed to the VLM such annotated frame. This help us to get more precise labeling, where the VLM answer that yes, the object number 7 is a chair, object number 1 is a wall, and so on. On the other hand, it also facilitates the opposite task, which is grounding. For example, I ask the VLM which object of these is the printer, and it answers that object number 11. One important thing that because we added this technology is actually the referring segmentation, which basically we know exactly about which object we are speaking. For example, VLM would say object chair number 6 is in the front of laptop number 9. So we are now know that we are speaking about this object, not about this, which is it was like bottleneck for us using our previous pipeline that I will tell you. One more important thing, it's handling small objects actually, because having a mask, we are like highlighting the VLM to tell me the name of small object, but in the opposite case, VLM would ignore such kind of objects. So having such technology is a key element within our pipeline. It's pretty straightforward and easy to get such a map. We have a raw image. We use mobile SAM, for example, to make things faster. We can have like 100 frames per second to get such images if we use mobile SAM with SOM. It's only about drawing colored mask over the objects with labels. It could be not only colored masks, but boxes, bounding box. Basically, the robotic system without it would struggle to define accurately the small objects. And it also we will get much more precise location, spatial relationship, I mean, between these objects, and we improve the visual grounding when, for example, here we have several cups. I say I need the mug with the circled black on the top of it, so the VLM will return for me exactly this one, not another cup. Yes, the previous method basically was the VLM based, where we feed a raw image, not annotated one, directly to ChatGPT. It tells us about what objects we have, but then we use it grounding Dina to do visual grounding for each object. But the thing is that the grounding Dina not always found the same object that the VLM meant, which made inconsistency in the answer and noise, the errors basically. And the result, all of that has been solved using, of course, about small objects has been solved using SAM-SOM, where first of all semantic. We filter these masks to get only needed mask about the objects without noisy masks. I mean, then those to SOM that annotated, and then to ChatGPT model, and then to line graph that extract out of the caption that we get an initial graph. So basically the caption looks like this. The context is that yes, we are here seeing a kitchen that contains these objects: plate number 1, apple number 2, toaster number 4. We get also unknown object because I made a prompt to the GPT-4o model that if you are not certain about any object, just say it's unknown. We avoid it. And some relationships. Well, line graph using also another kind of prompts using an LLM, it provides us with initial graph that being extracted out of this, where we have the objects are located inside the kitchen, and how these objects are related between each other. Now, another component, which is knowledge mapping, that creates a global knowledge map out of local knowledge, local observations, to get our 3D knowledge map that we can query of it, that we can use as a memory for the high-level planning. To do such a thing, we need to make a decision. This decision whether to merge or to add a new object if we see an object from another angle. Basically, to make such a decision, we need to calculate several kinds of similarities, such as visual similarity, geometrical similarity, and textual one. The visual is to compute the similarity between Dino or clip embeddings that each node of object stores in the current observation with the all embeddings of clip or Dino or both together to decide whether are the same object visually similar or not. Geometrical similarity is to calculate overlap between point clouds and intersection over union between them, between what I see now in the current observation and what I already have, while the textual similarity is to check the similarity between the labels using clip model, the label that I have and the label that are stored within the we aggregate all these similarities. We have kind of criteria whether to add a new object to the map or merge with already mapped objects. By this, we avoid duplicate objects. We update basically the attributes of the nodes, such as embeddings and relations, throughout the mapping process. So the outcomes, actually, the results of such system is what we see here in this rerun visualization. Here we see the objects, the relation between them. Each node has its information about crop, about caption of each object. Through that, we can do object search by, for example, here we had textual query of fridge, and indeed we localize it to the refrigerator, while we have the label as refrigerator, but we were able, using clip similarity, to find it here, to localize where we are in the map also, and we indeed integrated this system into the robot, and we were able to query, but this time not a textual query but a visual one, to send an image this robot to send, as we see, we send an image of the robot, of another robot, while the first robot made 3D knowledge representation as a memory. It found the needed object and went into it. Based on that, such kind of memory is the work of both planners, the global and local one, because the global, when we ask it to go to this robot, the global was able to retrieve where is this object is, and then for local planners, when we are approaching it, we can get a semantic waypoint that represent the 3D centroid of this object, so that we can move into it. Yes, it works normally, but such kind of graph representations and graph basically and such pipelines still have some bottlenecks. For example, it's some concerns about the performance. We have several foundation models which is not very suitable to real time. Some noises, hallucinations may provide some error that can accumulate throughout the mapping, and the consistency of the mapping process is challengeable through the time of the mapping. Moreover, the graph is only text, so that our planner interacts only with text, which may limit to some extent some functionality of it. Instead of we used not text, for example, images. And very important bottleneck here is the abstraction, because for example, if we say cup on table, we know information only that a cup on table, but what kind of table, what material it is, what is the color of the cup, how they are oriented, like placed on the table, we don't have such information from only this sentence. Moreover, the relation that I mentioned that we see here, they are limited as well. This limits actually the ability to make human-like decision, which because it's pretty hard to plan and do and solve a task having such kind of information. So one of our current hypotheses, very important one, is to move from symbolic representation by means of textual graphs to visual frames or visual memory, because we will have richer context rather than having only text. We have information about appearance, relationships, lighting, occlusions, background objects, and so on. This will make things easier for VLM if we will use it instead of as a global planner instead of an LLM. So no need for symbolic representation, no more need for like storing embeddings within the graph, which are very important to make the fusion, but are not important or not understandable maybe for an LLM. So basically, this doesn't mean that we are getting rid of graphs. No, it's not a replacement. It's only how we represent our information that are stored inside the graph. So we still need to build a graph, but how we augment these data So here we have, for example, augmented with IDs of the object. I could augment, for example, if the task is to find the toaster, for example, to say that the centroid of the, to write directly on the image, the centroid of the toaster has X, Y, and Z, to say the 3D coordinates, which may be helpful for the VLM. So to sum up, yes, we built a modular system that use object-centric 3D scene graph using open vocabulary perception. This pipeline combines several modalities and components such as foundation models, SOM, line graph, and of course the 3D fusion for mapping. We showed that we not only work it for recorded data but also on real robot. We did visual grounding and object search. We highlighted the limitation and some bottlenecks that still this graph holds, especially for downstream tasks. So our next hypothesis to move into visually annotated knowledge directly on the image to the visual large models. Thank you for your attention, and I will be very happy to answer your question. And see, thank you.
Малик, большое спасибо за ваш глубокий доклад касательно картографии знаний и их особенностей внутреннего строения и того, как это можно улучшить. Давайте, у нас сейчас время на один вопрос. Давайте выберите один и ответьте.
Ну, хорошо, я выберу вопрос от Сергея. Он спросил про ID объектов, которые SOM выдаются, уникальны ли они на самом деле нет. От локального графа в другой они могут быть разными, но это все бывает консистентно. Они уже на этапе создания локального графа, а вот на этапе глобального графа, где там даже если они похожие объекты, то у нас есть 3 разных критерия для определения схожести. Одна из них это по геометрии, где они расположены, и вторая по визуально. По визуально они, да, могут быть одинаковыми, но мы берем еще и бэкграунд, то есть мы расширяем, мы не только берем маск объекта, берем еще маск и то, что есть за ним, и делаем энкодинг. Кажется, что такой подход снижает такие ошибки, но у нас не получилось, что... Ну, то есть у нас бывают разные айдишники для объектов, даже если у них визуально все схожести. Да, у Сергея Ленока тоже был...
И что у нас сейчас времени на онлайн-ответы уже не осталось.
Хорошо,
в чатике. Да, большое спасибо еще раз за ваше глубокое погружение в картографию знаний. Будем ждать вас в следующем году. Благодарю.
Спасибо большое.